Hey, hello, and welcome to another Code Unboxed session. Today's going to be a little bit different. It's our 1 year birthday, so we've been doing Code Unboxed events for a year, and in that year, it has been quite a lot of fun talking through some of the bugs and issues that the team has found. Interestingly, the team has found over 30 odd bugs across multiple open source code bases. And we're going to talk a little bit about some of those learnings that the team has found today. So with me today, I have Roland and Clement. Roland, Clement, thanks, guys. I know you guys have done the majority of all of the heavy lifting on the code analysis, and thank you for joining today.
Well, it's a pleasure. I'm sure we'll find more coming in the next year, but let's talk about those this year at least.
Yeah. So, just as always, as we get started, if this is the first time you've seen Code Unboxed, what we do at TrustInSoft is our analysts on a periodic basis do evaluate open source code to identify if there's any, if there's any memory related bugs within that code, and we then disclose those bugs to the respective application or code owners. We do follow a 90-day disclosure policy, and we want to be respectful and make sure that any of the code owners do have time to resolve or address any of the respective memory-related issues that we do identify. So as we get into it, if you don't know much about TrustInSoft, at a high level, TrustInSoft, we are a code analysis company, so we help developers. Really, our mission is to help developers deliver mathematically proven zero defect product or zero defect code. All right. So how do we do that? We provide a code analysis tool, and that code analysis tool takes advantage of formal methods and abstract interpretation, which ultimately results in what we call exhaustive static analysis. So, Roland, if you wouldn't mind, can you elaborate a little bit more on exactly what I mean by the formal methods and the abstract interpretation and exhaustive static analysis for those who are not aware of those respective techniques?
Well, first of all, it's exhaustive if you want to. And if you want to stop before exhaustiveness, then you can as well. That's part of the thing. And so in the Code Unboxed, actually, we showed the first stages of setting up the analysis and how you can find bugs early on. And then obviously, one of the things is that if you can reach the end of it, that is something that not many pieces of software allow you to do. So what the kind of issues you can find with TrustInSoft Analyzer are the kind of bugs that relate to really the true behavior of the code as it would execute on the target, and the typical bugs that are not found during testing. So that would be memory-related issues like buffer overflows or use after free or special pointer incorrect management. That can also be bad computer calculation, so typical overflow or underflow in the calculations. And so the way it works is it's like Gavin said, it's like you said, it's a formal tool. So the way it does it is it reads the code. It will create in memory a graph of the code. Then it will start with the initial value and the input data that you give it into, and then start to go through the graph of the code, instruction by instruction, and state by state. In doing so, it's kind of like an execution or a simulation, except it's a special simulator because you can give it values like you do usually, like minimum, maximum, median, and so on. But you can also give it ranges of values. And so that's great for regular testing. But in fact, for cybersecurity, this is awesome because that means you can actually test for all the values in one go, or ranges of values in one go, as you see fit. And that means ultimately, if you use it,
which probably saves a ton of time, right?
Well, of course, because instead of doing millions and millions of tests like fuzzing, I think Clément, you're going to mention that, right? Instead of doing that, you can do that in a much more contained time and do one time all the values. So that will usually complete in seconds or minutes, not days or not in infinite time, because you never complete the work. Again, exhaustiveness is one of the things that we can reach. And that's something where some people would think that formal methods are really heavy, but in fact they're reasonable. That's approachable, and that's why it was fun to do those videos. Really,
it's interesting. I was just thinking, you talk about testing from maybe an infinite number of tests, but we're doing that in a matter of seconds. So that's, anyway, I know you guys are going to talk a little bit more about that, but that's the beauty of math. Try and wrap your head around that, and that really is the value of formal methods, ultimately, by applying that to code analysis. Why don't we change gears and maybe get into a couple of the analyses that you performed then? And I think Clément, you did one of the first ones, and that's around TinyCrypt. So could you talk through a little bit about some of the bugs you found in TinyCrypt and the analysis, just as a quick recap?
Yeah, sure. So yes, our first code unbox was actually on TinyCrypt. It was to showcase how easy it was to set up the analysis. And indeed, with TinyCrypt, takes very little time to get to some bugs. In total, we found 6 bugs in TinyCrypt. Most of them are pretty small. Some integer overflow, where most developers don't actually know the ins and outs of the C standard, and they do operations that are valid in most contexts, and they just end up to being invalid in some very confined context. We did find something interesting in the HMAC module, where a mitigation for a timing attack actually introduced a different kind of attack where you could start to leak data. So that emphasizes the fact that with cryptography, you can be attacked from all sides, and you really need to be thorough in checking, and that's what we allow. And also, slightly more interesting, we found that there was a small bug in one of the tests. And while the consequences of the bugs are probably nothing, because it's in the test, not in the production code, it still invalidates the test. And so you also need to think about that, the fact that your own tests could themselves have bugs. And the approach that we have at TrustInSoft really helps you detect all of that at once. And I think that's beautiful.
So wait, did I hear that correctly? That we actually found security-related issue in the crypto stack?
Yeah. You would still
which is
relate
not
that
resolved yet, right?
Yeah, so TinyCrypt is a bit abandoned now. It's been abandoned by Intel. It says so on the GitHub page.
Yeah.
But yeah, if you do find a crypto stack that still includes TinyCrypt, we know about some failures in there. We can point them to you.
So just on TinyCrypt, because that one is important. I found after we recorded the video that Zephyr has been using TinyCrypt until about 6 or 8 months ago, and that was that was the standard crypto stack, in fact. So now they've moved on to Embed TLS, where we actually did an analysis on a previous version of Embed TLS and proved that there was no runtime error. But that's something I found also that is still used in Nordic semiconductor framework. So it is still used out there, actually.
Yeah. So public announcement, if anybody's, if you're watching this and using TinyCrypt, you might want to consider moving on. That's an interesting point. I guess on the theme of moving on, why don't we switch gears to embedded operating systems? And I know, Roland, you did some work on Trampoline OSEC.
Yes.
You want to talk a little bit about that as well?
The reason we chose trampoline is that we wanted to show that it's possible to analyze an operating system. Operating system is always a difficult piece of work because there's scheduling depending on where you are in the world. There's all a matter of things happening concurrently. And also we wanted something slightly automotive flavored. And so trampoline was an interesting one. We did find a few things there, especially during the init phase and then in one of the drivers. So nothing too critical, really. Probably those issues would never be encountered in a real deployment. But still, it was a demonstration that you could use the tool on an OS. You can use the tool in the automotive world. Actually, the tool is qualified for in automotive, and it wasn't so hard to set up. And we did find 5 bugs total, 5 bugs.
Okay. So nothing too alarming there, though.
No.
Okay.
No, but at the same time, this is an open source OSEC. It's actually a well-known reference as an OSEC. I don't know if so many production projects actually use it. The message is actually to all the other vendors. We're happy to work with you also on production code. And we're working in the automotive field, and our tool is used to find bugs.
Fair enough. So then why don't we, Clement, you did analysis on libgit2, and I know one of the common use cases for libgit2 is providing API access to Git repositories. So why don't, hopefully you didn't find anything related to that from a memory leakage perspective or bugs, but if you want to talk through your experience with libgit2 as well.
Yeah, so in libgit2, which is not the main Git implementation, but it is used in some other applications that may interact with Git repositories. We found 3 bugs. 2 of them were null pointed references that just came up from a function isn't checked for error, and so you have initialized buffer, you have null pointer propagation. It's great that the analyzer is able to tell us not only it tells us it helps us really easily find what the problem is, where it happens, where it comes from. But also, like Roland said, the analyzer really is testing multiple values at a time, and that allows us to, out of the box, really test at the same time the success case and the failure case. And so we get those essentially negative tests of all sorts of APIs. We get them for free, so we can test for failure from any sensor, any dependency. We can test for failure by simulating a runtime that can fail while still getting results when it doesn't, which is really hard to do with regular testing. You mentioned memory safety. We did find a pretty interesting bug in libgit2 where by calling an entry point and then triggering a file system issue, maybe by doing a networking issue, maybe by switching the hashing stack, the cryptographic stack under libgit2, you could trigger a bug, and that bug would essentially read some data off of the stack and pass it to some other part of the application. And really at that point, the data is completely out of control. So possibly an attacker could trigger that bug and make your application, the application that's linked against libgit2, start to read off data that it's not supposed to read. And by then, the consequences are completely out of hand. We would need to look at the actual application to tell you what the consequences would be, but we can already tell you that libgit2 could have been used in a successful attack by being the trigger in a series of attacks.
So moving on then, I know we spoke a little bit about fuzzing earlier. And Clement, you did an interesting exercise where you were combining fuzzing with our TrustInSoft analyzer, and you did some analysis on libjxl. So how did that all pan out? And you want to talk a little about how that worked out?
Yeah, so libjxl was a library meant to handle a kind of new format for large JPEG images. And also in there was a new implementation of a regular JPEG library called JPEGly. Since then, it's been moved into a Google repository. But when we did the analysis, it was part of the scope. And we chose libjxl to showcase fuzzing with the analyzer, because libjxl is one of those libraries where you really expect very, very structured data as input, right? You can't truly give off ranges. We get into a problem issues with precisions with the analyzer and so on. So it was really a good candidate for fuzzing, where we have a bunch of buffers that each have a structure, and then it's up to the library to say those buffers are invalid, those buffers are correct, here's the data that I handle on such and such buffers. Yeah. And so this was a really good candidate to showcase the integration of the analyzer with fuzzers. And we found 6 bugs. So 4 initialized memory issues. There was an initialization visitor of a tree, and it happened that that visitor was actually reading off the data it was supposed to initialize. And so that ends up with initialized memory issues. We also saw 1 invalid pointer arithmetic, probably for optimization purposes. They were doing some computation that doesn't make sense for all buffers. And so, we did eventually, with fuzzing, find some buffers for which it was never valid. And we also found in JPEGly this time a really interesting bug. It was a kind of an intentional bug. It would be removed by optimization. And I guess the developer was relying on the fact that this, so it would be a bad pointer computation. That computation was indeed removed by compilers. All compilers we tested under the correct, the optimization levels that they were using in JPEGly. The problem is, you're still relying on some behavior from the compiler, which is actually not stable, not defined. Tomorrow, you update your compiler, you just change compilers, you change your compiling stack, you get a different result. Maybe you don't get the same optimization. And this one was especially painful because we found that if you use a sanitizer, with optimization, it would also miss the bug. It would detect it at optimization level 0, but at any optimization level higher than 0, because the compiler was already removing the invalid pointer computation, the sanitizers would miss it. So that's really a place where TrustInSoft shines. TrustInSoft analyzer is really a perfect sanitizer. It does not miss any of the things that it claims to find. And so here in this case, it did not miss the invalid pointer computation.
Because it works on the source, right?
Yeah, because we work on the source and not the compiled source, so either assembly or binary, like a lot of other dynamic analysis tools do.
Yeah. That's a good point on, how do you combine TrustInSoft Analyzer with, even if you have a fuzzing implementation within your environment. So it's actually, I'm glad you spoke about it in detail, because that's a very good point where 1 + 1 does actually equal 3 in this case. So definitely not last but not least, Roland, you did. I think this one is probably the one that you got most excited about, because you do have an affinity toward mechanical keyboards, and you did. There we go. And you did an analysis on your favorite keyboard. Why don't you talk a little bit about that?
Actually, I've got both here.
Oh, there we go. Yeah.
Well, so that one was fun because I was looking for something that looked like an IoT device, and to analyze, and turns out that Keychron has followed the the great movement of using that open source firmware QMK. And so the question was, can we analyze that? And turns out that we can. It was also the longest video because there's a build system. The analyzing it is really the true analysis of a complete embedded system. But we could reach something that was fine in about 40 minutes and actually find some bugs as well. And those bugs actually, I think, is one of the bugs that I could actually reproduce on my keyboard, where you tap at it really too fast, then there would be a buffer overflow somewhere in the tapping. So
the workaround is don't type fast, right?
Yeah. Well,
okay.
Well, actually, the workaround is don't enable the RGB LEDs for lighting, but that's sad. You lose most of the fun of using that kind of mechanical keyboard. The point is actually it still managed to analyze about 170 files with 800,000 of lines of code in less than 5 minutes. And that's something that's also telling when you look at formal tools. Usually you don't scale. It's looking at very tiny pieces of code, like tens or hundreds of lines of code. The biggest OS that was formally verified is about 7,000 lines of code. And here it's a complete firmware that we could take on in less than an hour. So that's telling. So yeah, we found, yeah. And I'm sure we could find a few more things there. Well, there you go. At least it was successful fishing.
I think it was a fun project as well for you.
Yes.
Seeing it is one of the items you do collect. So, and that's it. I think that's all of the Code Unboxed.
We actually forgot. There was another one. Gnode.
Did I forget Gnode? Oh, thank you.
Yeah.
So why don't we talk about Gnode then? I completely missed Gnode. Sorry.
That's fine. That's why it's teamwork, right? So Gnode is a little bit different again. So that one was everything that we've talked about so far was C code. Sometimes embedded, sometimes for desktop or servers. This one is a C++. And well, that's another pet peeve of mine, is that I have been following Gnode since the beginning because it's a secure desktop platform or secure embedded platform. And because it's in the words, it's supposed to be secure. The question is, could we actually challenge that? And C++ has another challenge, that it's very expressive. It's very hard to analyze C++ code. And on top of that, Gnode actually uses modern C++, C++ 17 and pieces of 20. So that was an interesting one. We did find a few bugs, but nothing of the security level like Clément was talking about earlier. It was really corner cases of things that were actually okay with the specific compilation process that they were doing. Well, ultimately, as we communicated that to Gnode, to the Gnode people, all the issues have been actually resolved. So there was a potentially uninitialized variable during destruction. There was something about the size of a type that would be specifically potentially misaligned with the real type that was underlying there. It's kind of a placeable template around a regular type. And so the two of them were actually solved pretty quickly. And through a ticket, you can trace that. The third one took them a few months, and actually they put it as a bigger feature of complete reshaping of the init code. And that one was also really surprising. The code actually mentioned an explicit null pointer dereference. So literally *null PTR, which should never compile. passed as an argument. It should never compile, but actually Clang and GCC are just both okay with that. So somehow, again, that led into a bigger rework of Gnode, and well, not the latest, but the one before, of their release notes. They mention that reshaping. So all in all, it was good. And we did find a few things again.
Good, thank you. And again, I don't know how I missed that. We were meant to be talking about that earlier, but thank you for keeping me honest.
No worries.
Well, if you've been following along, by all means, just go to our website, TrustInSoft.com, and or look at any of the other Code Unboxed videos. And if you do want to participate in any of our Code Unboxed events and have us analyze your code, by all means, please do reach out to us. Contact details are available on TrustInSoft.com.
And if you want pieces of software to be analyzed, please say in the comments. We'll look at them for sure.
Yeah, exactly. Thank you, guys.
Thank you.
Bye.
Bye.